Ionic and molecular compounds. So there's two different types of compounds that exist in nature. We have ionic compounds and molecular compounds. Molecular compounds are when two or more nonmetals bond together. Molecular compounds form very strong bonds known as covalent bonds. And covalent bonds refers to a type of bond that's formed when there is a sharing of electrons between neighboring atoms. So instead of one atom giving up electrons and the other one taking the electrons, there's an equal sharing of electrons. I like to make the analogy of marriage. So when you get married, you share everything. Covalent bonds are like these atoms are getting married. So everything is being shared, and it forms a very strong bond. Ionic compounds are typically between a metal and a nonmetal. And the metal and nonmetal are going to interact in a way such that the metal typically gives up electrons and the nonmetal takes electrons. Ionic compounds form ionic bonds. And in ionic bonds, I like to refer to this as like a toxic dating relationship. One person gives, the other person takes. And it's not a very strong relationship. So they hang out near each other because they have opposite personalities. One gives, one takes. But it's not necessarily a good relationship to be in. And as soon as a better relationship comes along, they're going to switch up partners. And we can talk about that, especially when we get into series like reactivity series and single displacement, double displacement, precipitation reactions, all those different types of reactions. I'm going to keep coming back to this analogy of marriage, the covalent bonds, versus the toxic dating relationship, so ionic bonds. So molecular forms molecules and covalent bonds. Ionic forms ions and ionic bonds. In ordinary chemical reactions, the nucleus of each atom and thus the identity of the element remains unchanged. Electrons are actually going to be participating in chemical reactions by being gained, lost, or shared. The gain or loss of electrons results in the formation of ions or ionic bonds, but the sharing of electrons results in molecular compounds, which have covalent bonds. So this is a picture of a typical atom, and you can see the nucleus in the center with the protons and neutrons, and then the electrons exist on the outside as an electron cloud. When we have sodium as an atom, this is the size. It has 11 electrons, and it is this large. But when sodium loses an electron and becomes an ion, remember, if you lose an electron, you're becoming more positive because you're giving up the negativity. When you lose an electron, it becomes smaller. So we're going to draw out some examples now of different types of atoms of elements to show you how this interaction happens. So this is just in here as an insert for reference so that we can go back easily and reference the periodic table. But first we're going to draw out sodium. So sodium, going back to the periodic table, sodium has 11 protons. And because it has 11 protons, it's also going to have 11 electrons because we're talking about an uncharged atom. Now we go back here and we see that sodium has an atomic mass of 22.99. We're going to round that to get our mass number of 23. So if our mass number is 23, the number of neutrons is 23 minus 11 to give us 12. So protons and neutrons are going to be found in the center. Now what I'm going to do is draw it like this, because then I can use different colors when I start to draw. So we have protons, neutrons, electrons. So protons, let's do blue. So we're going to do 1, 2, actually, what color is this? Let's see. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons. Now we're going to do 12 neutrons. One, that's not that good of a contrast. Let's do this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 neutrons. Now when it comes time to drawing the electrons, electrons are going to exist in rings in a cloud that orbit that central nucleus. So the first ring can only hold 2 electrons. So we're going to put 1 and 2 electrons. So we have 11 electrons total, so far we drew out 2 electrons. So we're going to add another ring. Every subsequent ring can hold 8 electrons. When I draw out my 8 electrons, I like to go around clockwise, and I distribute 1 in each of the 4 corners, and then I distribute the second in each of the 4 corners as far as they allow. So we have 2 already. That means that we have 9 electrons left to distribute. The next row can hold 8, so we actually are going to fill up this whole second ring here. But I call this the 4 corners method. That's probably not an official name of this. I make up a lot of names to help students, remember the method for doing certain things. But we're going to do my 4 corners method of assigning electrons. So I'm going to put 1 here. 1, 2, 3, 4. And then I'm going to put the second one right next to the first one. 5, 6, 7, 8. So now we have 10 electrons drawn out. We've got the 2 in the first ring, the 8 in the second ring, so we have to put 1 more ring. And this one only has 1 electron on it. So 1 electron in this outer cloud. When we have 1 electron in the outer cloud, this 1 electron is lonely. And again, I go back to relationships. This one doesn't like being alone by itself. So when it's by itself, it feels uncomfortable. It would prefer to have all 8 on the outer shell. So in order to make this one happy, it wants to either gain 7 electrons, or it wants to leave and go join with someone else where it can be happy and it can be paired up on another atom. So if we draw chlorine, and I think chlorine is next, chlorine from the periodic table, chlorine is here. It has 17 protons. And since it's uncharged, we have 17 electrons. And neutrons, when we go back to chlorine, chlorine has a mass number, or atomic mass, sorry, of 35.45. So we're going to round that to 35. 35 minus 17 gives us 18. So that's 18 neutrons. So now instead of drawing out everything in the nucleus, I'm just going to draw the nucleus like a big circle. And we know that there's 17 protons and 18 neutrons in that central circle. But now I'm going to draw out the rings to distribute the electrons. So the first ring, if you remember, this first orbital can hold 2 electrons. 1, 2. The next and subsequent orbitals can each hold 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now all these are happy. They're by each other, they're paired up, they're good. So now we have 10 electrons here, so we actually have to draw another orbital. And this time we have 7 electrons left to draw. So 4 corners method, 1, 2, 3, 4, 5, 6, 7. So we have 7 electrons in the outer shell. For sodium, we had 1 electron in the outer shell. When you have electrons in the outer shell, those are called valence electrons. So sodium has 1 valence electron, while chlorine has 7 valence electrons. And electrons I sometimes abbreviate E-. Many people do as well, so if you ever see E-, you know that we're referring to electrons. So right now sodium is unhappy because this one's all by itself. Everybody wants to get married in the field of chemistry. So this one's sad, it's all lonely all by itself. This one wants to find a partner. In this shell, these two are a couple, these two are a couple, these two are a couple. This one is lonely, it's all by itself. Now in order for an atom to be truly happy, it wants a full outer shell. So as I mentioned previously, this one's not happy, it wants a full outer shell. But if this one were to leave, then it would have a full outer shell. But we can't just get rid of an electron without changing something over here, changing something with our math. If we did get rid of an electron, this would then become Na1+, or just Na+, because we're becoming more positive by 1. We're giving up that electron. This is the basis for how ions are formed. So I'm setting the stage by drawing out the pictures of the atoms. Eventually we will see how these bonds are actually formed. So when we're giving up an electron, we become more positive by 1. Now with this one wants a full outer shell. Now it can either lose 7 electrons, which would be a lot of work, or it can just gain 1 right here, and then everyone would be happy. Well, because sodium can easily give up an electron, and chlorine wants to accept an electron, sodium and chlorine like to come together to make sodium chloride. I'm sure you've seen or heard of sodium chloride before. Sodium chloride is your common table salt. So that's the salt that we eat every day on our food. So when sodium loses this electron, chlorine gains that electron. Chlorine can become then an ion. So if you gain an electron, you're gaining a negative charge. So that's Cl1-, or we can just say Cl-. Now we're going to draw nitrogen. So going back to our periodic table, we see nitrogen here. Nitrogen has an atomic number of 7 and a mass number, if we round this atomic mass, of 14. So nitrogen is going to have 7 protons, and because it's uncharged, it's going to have 7 electrons. And then because the mass number is 14, we take 14 minus 7 and we get 7 neutrons. So we're going to draw out our nucleus in the middle. And just know that there's 7 protons and 7 neutrons in that nucleus. And now we're going to draw out our electrons. The first ring is going to contain 2. The second ring we already used up 2, so 7 minus 2, we have 5 left. So we're going to distribute the electrons. Using my 4 corners method, 1, 2, 3, 4, 5. So everyone wants a partner in chemistry, so we have these 2 that are together and happy, but these 3 are unhappy. These 3 want to be happy. They want to form a bond with something else. So nitrogen has the ability to form 3 bonds. Okay, so I'd like you to pause the video, and I would like you to just draw out the atoms of the following elements. So step 1, you're going to determine how many protons, neutrons, and electrons. Step 2, you can just draw a circle in the center for depicting the protons and neutrons. But then you're going to want to draw the electron rings accurately. Remember, the first ring can hold 2 electrons, and subsequent rings can hold 8 each. So go ahead and pause the video and try to draw these out. Okay, so let's start with calcium here. So calcium on the periodic table has an atomic number of 20, so that means that there's 20 protons in the nucleus. And because it has an atomic mass of 40.078, we can round that to the atomic or mass number of 40. That gives us 20 neutrons. So we can draw a central nucleus that has an assumption of 20 protons, 20 neutrons. But now we're going to draw out the rings of the electrons. So we have 20 protons, and since this is uncharged, we're going to have 20 electrons. So in our first ring, we're going to have 2, 1, 2. In our second ring, we're going to have 8, 1, 2, 3, 4, 5, 6, 7, 8. We're going to have another ring, because so far we only have 10. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So now we have 18. So in our final ring, we're going to have 2 electrons. 1, 2. Both of these are unhappy. Both of them want to form pairs. They can't form pairs with each other, so they're going to want to go somewhere. And again, we're setting the stage for how bonds are formed. But that's our final drawing for calcium. The next one is fluorine. So fluorine has an atomic number of 9, and it has an atomic mass of 18.998, which we can round to 19. So we can draw the central nucleus. And I'm just going to put the letter F in the center for fluorine. Now we're going to draw our rings with our electrons. So since we have 9 protons and it's uncharged, we're going to have 9 electrons. So we're going to draw 2 in the first ring, 3, 4, 5, 6, 7, 8, 9. So these are paired up, they're happy. This one is unhappy, it's alone. That's our final drawing for fluorine. And now we're going to draw lithium. So lithium has an atomic number of 3. The mass number that's going to be rounded is 7. So in our nucleus, we have 3 protons, 4 neutrons. And I'm just going to put the Li in the center for the symbol. And now we're going to draw our rings. So since we have 3 protons, we're going to have 3 electrons. So 1, 2, and we have one ring that only has 1 electron. And this one's really unhappy. So it wants to leave, leaving the full outer shell for lithium. So predicting ion charge. The periodic table can serve as a guide for predicting the ion charge of main group elements. Many main group metals lose electrons to leave them with the same number of electrons in an atom of the preceding noble gas. So group 1 would lose 1 electron to form a cation with a +1 charge. Group 2 would lose 2 electrons to form a cation with a 2+ charge. Cation, as I defined previously, I mentioned that cat positive, cats are good things. I have 6 cats at home. So cation has a positive charge. Anion, think of like anarchy, that's a negative thing. Anions have a negative charge. So many nonmetals gain enough electrons to give them the same number of electrons as an atom of the next noble gas. So group 17 gains 1 electron to form an anion with a -1 charge. Group 16 gains 2 electrons to form an anion with a 2- charge. So for example, with calcium, group 2, calcium has 20 protons, 20 electrons. If it loses 2 electrons, it becomes more positive by 2. So the ion would be Ca2+. Bromine is in group 17. Bromine has 35 protons, 35 electrons. If it gains 1 electron, it becomes negative by 1. Moving from far left to far right in the periodic table, positive charges of cations are equal to the group number. Moving from the far right to the far left in the periodic table, negative charges of anions are equal to the group or number of groups moved from the left of the noble gas. So this is a really good reference table for you to take a look at. If you look here, everyone in group 1 is eventually going to form a +1 charge. Why? Let's go back up here. So here is lithium, and lithium is in group 1. As I mentioned, lithium's unhappy right now because it has this single valence electron. In order to make lithium happy, this single valence electron would have to leave, leaving a full outer shell. So if we get rid of 1 electron, it becomes positive by 1. Lithium right here in its happy ionic state is Li1+, or just Li+. This next one, sodium, we drew out sodium first. That was our first example up here, where we saw that there was 1 valence electron. In order for sodium to be happy, this 1 has to leave so that it can have an outer shell that's complete. So if we give up 1 negativity, it becomes more positive by 1. And if you were to go down the row here, you would see all of these have the ability to give up 1 electron, and then they'd be happy having a full outer shell. You can predict the charge of the ion that's going to be formed based on the location on the periodic table. So everyone in this group is going to be +1, everyone in this group is +2. We skip over the transition metals because those are kind of weird. We go to this group, which is +3. Carbon is always going to be neutral. So carbon, like if we want to get to a full outer shell of 8, and carbon has 4 valence electrons, it can either gain 4 electrons or lose 4 electrons to get to that full outer shell. So carbon's kind of in the middle. It's not going to necessarily form a charge. It could be + or -4. But then when we get to this one over here, all of these are going to be happy if they lose 3 electrons. so become more negative by 3. Nitrogen, for example. We drew nitrogen here. So nitrogen has these 5 valence electrons. So these guys are happy, but this one wants to be paired up. So it's easier to gain 3 electrons than it is to lose 5 electrons. So in order for this one to be happy, it has to gain 3 electrons. Now when you gain 3 electrons, you're going to become more negative by 3. So N3 minus. And these are going to act in a similar way going down the column here. These are -2 or 2 minus, and these are -1. We drew out fluorine. Fluorine, you can see, had 7 in the outside. All it needed was 1 more to make it happy. So if we gain 1 electron, it becomes negative by 1. Going up to chlorine, same thing. It ended up with 7 in the outer shell. All it needed was 1 more to give it a full outer shell of 8 and to make it happy. So chlorine can be minus by 1, because when you add a negative, it's becoming, or if you add an electron, it becomes more negative. So again, you can draw out the electrons in the clouds, or there's an easier way of just using this table as a reference. And knowing the position of where it's located in the periodic table will help you deduce the charge that it's going to form in its ionic state. So how many valence electrons are present in an atom of bromine in the ground state, and how many does bromine need to gain in order to have the same electron configuration as a noble gas? So let's look at bromine. And bromine has 35 protons, so it's going to have 35 electrons. So if we draw out all 35, it's going to take us a really long time. We're going to have to draw lots and lots and lots of rings. We can figure out the number of valence electrons from the periodic table. So bromine is located here in the periodic table. You can see that right there. If we go up to this periodic table, you can see the group numbers. Again, we can definitely draw out the rings, or we can figure out the number of valence electrons based on the position in the periodic table. Everyone in group 1A is going to have 1 valence electron. Thus, everyone in group 1A is going to have the ability to give up that 1 valence electron. When you give up 1 electron, 1 negative charge, you're becoming more positive by 1. So your charge then, when you do form an ion, is going to be 1 plus, or just plus. Everyone in group 2A has 2 valence electrons. So in group 2A with 2 valence electrons, in order for those to be happy, they have the ability to give up those 2 valence electrons. So everyone in their ionic state in group 2A is going to be 2 plus. Then we skip over the transition metals. Again, I mentioned that those do some crazy things. We will be doing some stuff with transition metals as the class progresses, but those values will be given to you. You can't just make assumptions based on their location in the periodic table. So we go over here, we get to aluminum. Aluminum is 3 plus. So we end up with 3 valence electrons, and we can give those up easily. Everyone in group 4A has 4 valence electrons. Since 4, you can either gain or lose those 4 electrons to get to 8 outer shell. 4 is kind of like in the middle. We don't form ions with carbon. Everyone in group 5A has 5 valence electrons. If you think about it logically, is it easier to give up 5 or to gain 3 in order to become a full 8? It's easier to gain 3 than to lose 5. So here is where we start getting to the negative charges, because when you gain 3 electrons, you become negative by 3. Everyone in group 6A has 6 valence electrons, or 6 electrons are going to end up in their outer shell. In order to be happy, it wants to get to 8. So is it easier to gain 2 or lose 6? Obviously, it's easier to gain 2. So when you gain 2 electrons, you're becoming more negative by 2. Your charge is going to be minus 2. Everyone in group 7A has 7 valence electrons. To be happy, it wants 8. So is it going to gain 1 or lose 7? It's going to gain 1 because it's a lot easier to gain 1 than to lose the 7 you have. So when you gain 1, you become more negative by 1, so that becomes your charge. Now if we look at these noble gases, the noble gases in group 8A have a full outer shell. So with the exception of helium, which only has 2, but 2 creates that first full outer shell, all these other ones have 8 valence electrons. And when you have 8 valence electrons, you're happy. Everyone's paired up. Nobody wants to form bonds with anyone else. So that's why these are non-reactive. When electrons are shared or leave an atom, that's when bonds can be formed, and that's when reactions can happen. But if your outer shell is full, if everyone in the house is married, you're not going to be forming bonds with others outside of that marriage. So all of these are non-reactive. They're not going to try to react or form bonds with other elements. Now, based on what I just went through, you can see how it aligns with this table. I said that there's 1 valence electron in this first row. It's easy to lose that 1. When you give up a negative charge, it becomes more positive by 1. Everyone in group 2 has 2 valence electrons. It's easier to give up the 2 than it is to gain 6. So you give up 2 negative charges, you become more positive by 2. Then we skip over to here. I said everyone in this group has 3 valence electrons. It's easier, or sorry, 5 valence electrons, because we're in the 5th group. It's easier to gain 3 than it is to lose the 5 you have. So all of these are negative by 3. This one has 6 valence electrons, so there's 6 electrons in the outer shell. We want to get to 8. It's easier to gain 2 than it is to lose the 6 you have. So here we go. You can see the charges are 2 minus. And in this one, they have 7 valence electrons, so there's 7 electrons in the outer shell. In order to be happy, they want it to get to 8. So if we have 8, or if we want to get to 8, we need to add 1 electron. Adding 1 means you're becoming more negative by 1. And you can see the noble gases in this group. They have a full outer shell. They're non-reactive. They're not going to be able to form ions.